Okay, so like I said, we're looking at the worksheet. I'm going to go, we're pretty much going to go straight to 1C, but if we can answer 1A and 1B in class, that's phenomenal. So let's try and do that first. So 1A, or for question 1, what do we have? So we've got U16. Let's remind ourselves what U16 is, right? So it's 1, 3, 5, 7, 9. What should there be? There should be 8 elements, right? So 11, 13, and 15. Is that 8 things? 1, 2, 3, 4, 5, 6, 7, 8. Yep. Okay, so that's U16. And we've got H is 115. And that is a subgroup, right? Because 215 squared is 225, which is congruent to 1 mod 16. And we've got K is equal to 19. And same thing, yep, that is a subgroup. 9 squared is equal to 81, and 5 times 16 is 80. So this, again, 9 squared is congruent to 1. So for A, it says prove that H and K are normal. There's nothing that we have to do. Claim this is trivial. By the way, you're never allowed to write that word, right? That's for professors only. Students aren't allowed to do that. But why is this trivial, right? And of course, if it's trivial, you should explain why it's trivial. So why is this trivial? Nobody? Nothing? What is special about U16 that guarantees that H and K are normal subgroups? U16 is abelian. Every subgroup is normal, right? Boom, done. Nothing to do. If you wanted to, you would go through, and I'm certain if you actually started checking, like you started computing, 3H, 3 inverse, you'd be like, oh, hey, look, everything cancels out and I just get H back every single time. Why is that? Oh, because 3 and 3 inverse are canceling each other out, because obviously multiplication is commutative in the integers, right? So U16 is abelian, H and K are automatically normal. There's nothing to do there. B, also trivial. Maybe I'm being mean here, though, because maybe it doesn't seem trivial to you. Why are H and K obviously isomorphic? No one's brave enough? That's fine. First of all, you can just write down the isomorphism. Right? That's the only thing it could be, because you need to bijectively map, and the identity has to go to the identity. So 15 has to go to 9, and of course you can very easily check that 15 squared is equal to 1, which is equal to 5, 9 squared, or which is equal to 9 times 9, and that's 5, 15 times 5, 15, and that's the only one you have to check, right? But more importantly, they're both groups of order 2. And all groups of order 2 are isomorphic, right? They're all just Z2, right? They're definitely cyclic. So alternatively, H and K are cyclic order 2 groups. So are isomorphic, right? There's only one cyclic group of order n for any n. So that's how I would have done it. Don't bother to write them down. It's immediately true. Okay, so C requires some work though. So we want to look at G mod H, and then we want to look at G mod K, and we want to determine whether these groups are isomorphic, the quotient groups, right? So this is the interesting question. And this one, I'm going to give you a little bit of time to try. And what I would strongly suggest that you do, so both of them are the same size, right? What is the size of G mod H and G mod K? Like, what is the order of these? They're both equal. What is that? Lagrange's theorem. Not 16. Close though. What's the size of G? How many elements are in? I guess I should say U16 divided by H. But how many elements are in U16? Right, I wrote that up there. Right, exactly. There's 8 elements in U16. H has 2 elements. K has in 2 elements. Both of these are order 4. No problem. It was an easy mistake to make. Okay, so both these groups have order 4. Now, we have seen in the past that there are at least 2 groups of order 2. In fact, there are exactly 2 groups of order 2, or sorry, order 4. There are exactly 2 groups of order 4. So it is possible that these are isomorphic because they definitely have the same order. On the other hand, it's possible that they're not isomorphic because we know that there are multiple groups of order 4. In fact, there are multiple abelian groups of order 4. So we have to be a little bit careful about this, and it's quite possible that these are not isomorphic. Like all things, there's a couple of ways that you can show non-isomorphic. What I would strongly recommend doing is compute the orders of the elements of this group, right? Because if the orders don't match, right, an isomorphism has to preserve orders perfectly from the domain into its codomain. So what I would suggest doing is compute the orders of these elements and then see if they match. And if they match, that's a strong case for an isomorphism and tell you kind of exactly how to map things. And if they don't match, then boom, you're not isomorphic. Okay, so I'm going to give you a couple minutes to try that. And it's just computation, so see what you can get. All right, so work them out and see what you get. And then I'll take that up after and show you exactly what I think. And then even better is once you've done this, tell me what group and or groups U16 Mod H and Mod K are. Okay, so give that a shot. Okay, so that works out to be about 4.5 minutes. Does anyone have an answer? Are they isomorphic or are they non-isomorphic? Nothing? Okay, well then let's check. Let's find out. So what do we have in terms of the actual group itself? So let's look at U16 Mod H. Okay, so we're going to look at this thing. And we have, for sure, we have the identity coset, right, which is 115. And then let's just start looking at what the other cosets are. I think it really helps just to know what everything is. Okay, so I computed these ahead of time. So we've got 313. That's that coset, which is obviously the same thing as 13H, right? Because your cosets are equal if the generating element is inside of the coset. We have 5H is equal to 511, which is also equal to 11H for the same reason. And then we have 7H, and this is going to be the last one, is equal to 79. And that's the same thing as 9H. Okay, so these are our 4 cosets in this group. And let's start looking at the orders of these elements. Okay, so let's find these orders. Let's find the order of GH for each G. Okay, so I think it's actually best to start with 7H, just because, again, I've kind of done the work ahead of time and I know that that's going to be the best one. Actually, before we even say that, maybe let's remind ourselves that according to Lagrange's theorem, the order of these elements are either 1, 2, or 4. Those are the only options, right? So by Lagrange, everything has order, right? The order has to divide the order of the group. So it's 1, 2, or 4. And the identity element is the only thing that can have order 1. So in particular, 3H, 5H, 7H, whatever they are, they can only be order 2 or 4, right? Those are their only options. So whatever, let's start at the beginning. So if I take 3H and I square it, that gives me 9H, right? And that's, like we said, the set 7, 9. And since that's not the identity, I'm actually done. right? We know that the order of 3H has to be 4. But if we were to continue on, let's just do it in theory. 3H cubed. So that's 27. So that's actually 11H, right? Or 5H. We'll leave it as 11. And then 3H to the power of 4. Well, we know that anything to the power of the order of the group is equal to the identity. So this has to be H. So thus, the order of 3H is equal to 4, right? And if we continue on in this pattern, we would get that the order of 5H is equal to 4, and the order of 7H is equal to 2. Okay, so great, perfect. We found the orders. In fact, we found that there is an element of this group that has the same order of the group. So we know exactly what U16 mod H is. What is it? What group do we commonly know this as? What is it isomorphic to? Anyone? Right, this is Z4. It's a cyclic, it's an abelian cyclic group of order 4. It has to be Z4. Okay. All right, so that's the first case. Now let's look at U16 mod K, right? So we've got our first case, which is 1, 9. And then if we start computing, we're going to get 3K, which is 311, which is also 11K. We're going to get 5K, which is 513, which is 13K. And then we get 7K, which is 715. And that's also equal to 15K. Okay. And again, you can go through the same notions. And what you're going to find is that everything in here has order 2. Every non-identity element. So the same work shows that the order of 3K is equal to the order of 5K is equal to the order of 7K is equal to 2. And in fact, we remember that's exactly what happens in the other group of order 4, right? So we immediately know that these aren't isomorphic because Z4 is not or let's say there is no element here of order 2. This group is not cyclic, or sorry, of order 4. This group is not cyclic. So they're immediately not isomorphic. But we've seen another example of a group of order 4 that had exactly this property, right? Back in our very first group lecture, when we were talking about, I forget what it was, like U12 or something, we said U12 has this property that every element in it has order 2, right? Everything, it was definitely not cyclic, but it was a group of order 4. So yeah, not only are these not isomorphic, but this is a completely different group that we are familiar with. This group has a very famous name, but unfortunately, we just not at the point, for whatever reason, we kind of have left products until the very end of the course. This group has a very famous name, which I always want to say, but out of curiosity, does anyone know what this group is called? No one's ever heard of this? Let's put this as a little side note. You might have heard of this, just kind of if you've been around enough mathematicians, you might have heard it said. This is the Klein-4 group. Okay, so that's what this is. This is the group of order 4 that is not cyclic and is abelian is precisely the Klein-4 group, and every element in that group has order 2. And there's a very nice way of writing this down, which isn't U16 mod K or U12 or whatever the case could be. Yeah, exactly, right? You've probably heard of the Klein-4 group. It kind of gets thrown around and mentioned. In fact, if you've ever seen a finite simple group of order 2, which is this wonderful love ballad by a bunch of mathematicians, right, and this is what I'm saying. So what we're going to do, I'm trying to remember if we're going to prove it in this course, but there are precisely 2 abelian groups of order 4. One is obviously Z4. The other one is the Klein-4 group. And yeah, you don't want to obviously write it as U16 Mod K, right? That's kind of gross. Like that's not a great way of writing it. But we're going to see much later, maybe in a week. I guess there's only like a week left, but we'll see next week, I guess, how to write the client for group down in a way that is very manageable and very easy to understand. And so all this time, for the last 11, 12 weeks, however long it's been, that we've been referring to this special group of order 2, or sorry, of order 4, where every element inside of it has order 2, we were referring to the client for group, right? It is there. It's been constantly showing up in the course all the time. It's just we haven't referred to it as this, but it is the client for group. Okay. And by the way, does anyone know what I'm talking about when I say a finite simple group of order 2? Has no one ever seen that? Like that was a huge thing when I was an undergrad, but it might not be anymore. That's not what I wanted. All right, this is what I want. Okay, I'm going to assume that none of you have ever seen this. I'm going to find it for you. Okay, don't do this now. But when you get a second, watch this. Okay. All right. So I'm going to skip 2, but maybe we'll come back to 2 if there's time. 2 is just, again, kind of computational. Let's do 3. Okay, so question 3. This is a nice one. This one's actually really easy, but I think it looks really scary. So that's something to keep in mind. So H is a normal subgroup of G. And we're told that the index of H and G is 4, right? Show that G to the 4 is in H for all G. Okay, and the reality is that there is nothing whatsoever special about 4. Okay, 4 could really be pretty much any number. So show that this is true. This proof is 2 lines, maybe 1 or 2 lines. Like it shouldn't be very long. When I write it out, I might be a little bit more expressive than that, but it's a very fast proof if you see what to do. Okay, so again, I'm going to give you say 4 or 5 minutes and see if you can come up with the proof of this, but it should be very, very quick. And again, obviously think about what we're talking about in this week. That should be a big hint, right? We're talking about quotient groups, so maybe use a quotient group somehow. And you're told that H is normal, so you kind of have exactly the tool that you need to do that. But give it, 4 or 5 minutes and let's see if you can come up with an answer to that. Okay, so I think we're at 4 or 5 minutes here. We'll give it another shot. I'm not going to lie, I definitely watched the finite simple group video while I was waiting. I don't know if any of you did too. God, I love that video. It's so good. I must have taken until grad school for me to understand every reference inside of that video. I think at your level, most of you probably get about 1/4 to 1/3 of the references, I think, depending on kind of what your math background is, but there's enough in there that I think you'll smile. Even though you probably don't know what a principal bundle is or simply connected or anything like that. But you do know what it means to be in the kernel of a rank 1 map. So for what that's worth. Okay. So yeah, let's do this. And again, kind of there's a big hint here, which is you know that the index of H and G is equal to 4, and you know that H is normal. So you know exactly what the order of the quotient group G mod H is, and it is what? Right, exactly, it's 4. Right? Because that's exactly right. The definition of the index is that it is precisely the order of the set of cosets. And in this case, the set of cosets is the quotient group G mod H, right? So exactly, it's 4. And we also know that if you raise any element of the group to the order of the group, you get the identity, right? That was something that we had talked about when we proved Lagrange's theorem. We said as a corollary, if you raise any element to the order of the group, then you get the identity back. So this is our key here, is fix some G and G. And look at the coset that it generates in G mod H, right? So if I raise this thing to the power of 4, which is the order of the group that this coset is in, I must get the identity back, right? So H is equal to G to the H to the power of 4, which is by definition, G to the 4 times H. And if you look at this, what is the only way that this is true? Well, G to the 4 has to be an H. And that's what we wanted to show. So we're done. Right, and again, you can see there's nothing special about the number 4 there, right? We literally could have used any number and this would have worked out. So yeah, there's just something to keep in mind. Push down to the quotient. That is the order of the quotient there. So if you raise it to that number 4 in this case, you get back the identity, and being the identity is equivalent to saying that you are precisely in the normal subgroup, right? So that's 3. Are there any questions about that? So far, so good. Okay, question 4, we're going to skip because I already did it. I actually totally didn't realize that we were going to do it as part of the worksheet, so I did it as part of lecture. So C, Tuesday's lecture. I think this is, or not Tuesday, Monday's lecture. I think it was the very last thing I did, right? Where I said, take a look, you know, at this, these maps from like G mod H into G mod N, and then I composed them and looked at their kernels and all of these sorts of things. So I did precisely proof 4 on Monday. So again, if you want, you can go check out the lecture that we did then. So let's move on to question 5. Question 5 is again 1 line. Let's see if you can do it. Okay, so what do we know? We know that phi is a group homomorphism. And I hope that you're starting to get an appreciation. Like, I'm not trying to belittle anyone. So for example, if you're like, oh, you know, he says they're so easy, but I struggled with them, that's okay. I mean, again, it's going to be easier to me because, you know, I've been doing this for so long. But I hope that you're starting to see the power of the toolbox that we've built up, right? To the point where we can prove these results that seem quite complicated, and they're only a line or two of actual work, right? Because in particular, we're invoking some very powerful theorems. So phi mapping G to G is a homomorphism. And not the trivial map. Right? Otherwise, the theorem is obviously false, but that does end up coming up in the proof. And the order of G is a prime. Right? Show the G is isomorphic to its image. Okay. So give that a shot. Again, I'm going to give you like 4 or 5 minutes. This is 2 lines. This whole thing is 2 lines. So hopefully it shouldn't be too much work for you. Okay, any luck? Anyone managed to prove this? I mean, it's funny actually when you think about this theorem, because like you assume that yeah, whatever. Let's say this. Like, obviously, phi is not just isomorphic to its image, or rather, G is not just isomorphic to its image, but phi is in fact an automorphism, right? So in fact, we can prove that, right? So note, we will prove that in fact, phi is an automorphism, right? Namely that it is surjective. Do we need quotients for this? Not directly. All I know is the order of G is prime, so two subgroups in phi is not the trivial map. Okay, yeah, perfect. Okay, so right, Harvin, you're exactly on the right path, right? And the two subgroups are precisely G itself and the trivial subgroup, right? That's important. And then Paula, yes, but not directly. Okay, so here's the important thing. So Harvin, you've hit the nail on the head. The kernel of phi is a subgroup. In fact, it's a normal subgroup, right? Right? Right, sure, okay. But the kernel, you can always quotient by the kernel of a homomorphism, right? And that's kind of a critical point. So if you have a homomorphism, you can always quotient by the kernel. So the kernel has to be a normal subgroup. And as Harvin says, by Lagrange's theorem, the order of the kernel has to divide the prime. So it's either 1 or it's p, right? So either the order of the kernel as a subgroup is equal to 1 or p. Now, what happens if it's p? Then what have we said? Then we have the trivial map, right? Exactly, Paula. So that's the kernel of phi is then G, which, as Harvin says, then implies that it's the trivial map, and that's not allowed to happen, right? Kernel of phi is equal to G, so phi is trivial, right? But we said not the trivial map, right? So this isn't allowed. And that's not allowed. Okay, so that means that the kernel of phi must be equal to 1, which means what? All right, so the kernel of phi is just trivial, just the identity. What does that mean about phi itself? Just out of curiosity. Right, it's injective. Now, we actually don't need that, but in terms of like proving this question, but in terms of proving it's an automorphism, we do, right? But anyway, so the kernel of phi is trivial, and I'm just going to put in like yellow here. So phi is injective, right? Now, we don't actually know that. Okay, so by the first isomorphism theorem, G mod its kernel is always isomorphic to its image, right? But the kernel is trivial. So when you quotient out by the trivial group, you just get your group back. So G is isomorphic to its image. And we're done. Yeah. Right, there it is. Now, this is kind of silly because the image is actually G as well. Right? Note. The image of phi is actually equal to G. So there's a sense in which this is trivial because we've just shown that G is isomorphic to G, and that was obvious. But we could rephrase this as saying phi is actually an automorphism. So if you have a homomorphism with this property, it's actually an automorphism. So the image of phi is equal to G. Why is the image of phi equal to G? Can anyone tell me? Why is the image of phi equal to G? What does that mean? In terms of the homomorphism, what does it mean if I say that the image of phi is the entire codomain? What property of functions is that? Image is all possible outputs. Yeah, okay. And so Harvard, we have a word for that though, right? What does it mean that you hit every single point in your codomain? If I give you a function from A to B and every point in B looks like f of A for something, what is that? What do we call that? Exactly, it's surjective, right? Could we have said phi is an automorphism and it has trivial kernel, then it has to be surjective, right? And this is it. So because G is finite, if I give you an injective map between G and G, it must also be surjective, right? This is like a Math 102 thing. It only works for finite groups, right? It doesn't work for infinite cardinals, but an injective map between two sets of the same size must be surjective. Since an injective map between sets of the same size is automatically surjective. Right? So thus phi is actually a bijection because it's both injective and surjective. Okay. In fact, there's another way without using the first isomorphism theorem that this is trivial, that this whole problem is trivial, that everything that we've done, we didn't need to do anything. And the reason for that is when we learned Lagrange's theorem, we learned that if you have a group of order P, it's ZP. It's isomorphic to ZP, period. So if you give me now a non-trivial map between ZP and ZP, it has no choice but to be an automorphism, right? It has to be one. It doesn't have a choice. Right? And you can kind of, again, make that argument in exactly the same way, right? Because we said the order of G is prime, so it has to be ZP. And now if I give you a map from ZP to ZP, well, what are you going to do? That map has to, if it's not the trivial map, then it has to be a bijection, right? And you're done. So now it's an automorphism. But Paula, I guess I didn't read your comment strongly enough. We didn't know it was an automorphism to begin with. I'm using the fact that because it's an injection, then it's a surjection to prove that it's an automorphism. Does that make sense? Like I didn't know it was an automorphism. This is me, the yellow is me proving it's an automorphism, right? I'm just saying, yeah, there's a sense in which this is naturally true. So this whole question is kind of silly in the sense that, you know, we actually could have done it in a bunch of ways. We proved that G is isomorphic to its image, but its image is actually everything, right? Its image is G. And so that's kind of trivially true because G is always isomorphic to G. So we didn't really prove anything interesting there. But yeah, there we go. Okay, so yeah, we're not going to have time because obviously we only have 2.5 minutes. So we're not going to have time to do question 2. 2 you should do on your own though. 2 is not difficult at all. I don't know why B, like 2B is a question, other than maybe to give you practice using Lagrange's theorem, but you only need 2A to answer 2C, right? So, you know, do 2 on your own. It's a good little bit of practice just to make sure that you understand quotient groups. But yeah, I mean, if you know 2A, then you can answer 2C without too much trouble. Okay, everyone. So if are there any questions? Is anyone not certain about what happened? Yeah, no problem. And yeah, by the way, everyone, like the moment you see isomorphic to the image, you should think first isomorphism theorem, right? Like that's kind of the immediate thing that should come out there. Okay, well, if there's nothing else, AH equals BEH, but A is equal to B. No, so this is the order though, right, Harvin? So it's not saying that AH is equal to BH without A being equal to B, but it's saying that their orders are different. Does that make sense? So it's a slightly different question because absolutely, you're right. AH can be equal to BH with A and B being different, but do their orders have to be the same? That's sort of the interesting question, right? And so you're right, like it's not that much different than that, you know, sort of conversation that we had before. In fact, there's really no reason to suspect that their orders would be the same precisely because you know that A doesn't have to be equal to B, but nonetheless, it's a nice little exercise to be like, oh, hey, look, by the way, even the orders of the elements don't have to agree between cosets. Yeah, and I think it shouldn't be too hard. You can break it very, very quickly. So definitely give it a shot. But 2A does kind of set you up nicely as an example. If you want an example that you know for sure works, like if you take S3, for example, I don't think it actually works in S3, at least not with the usual cosets that we've talked about. But in this group, Z20 mod, the subgroup generated by 8, which is probably too big. You don't even need the group to be that big. But I can confirm for you for sure, because I did the problem, that group does work. And that, yeah, I mean, you can definitely find something that is in the coset 14 plus 8 that doesn't have the same order as 14. So you can just explicitly do it there if you want to know that you have an example that works. Right. But yeah, if you want to come up with another example, that'd be phenomenal, especially if you can come up with a smaller example, something that's not in like Z20, right? I think that'd be cool. Okay, everyone, thanks for coming. Have a good weekend, and hopefully I'll see you on Monday. Yeah, no, thanks everyone. I always appreciate those of you who have hung out and still managed to come. But yeah, I'll see you on the other side, and hopefully that should be the last-ish thing. Okay, see you, everyone.